Hey y'all. In the last video, we looked at some properties of different compounds based on the interparticle forces they experience. And today we're going to look at some really specific examples of ones that don't fit into those categories perfectly. Today we're going to look at network covalents, polymers, and alloys. So let's go ahead and get started. We're going to start by looking at network covalents. Network covalent compounds are those that are comprised of non-metal elements, which are covalently bound into a network. So it's not as simple as a single molecule, but instead is a network of seemingly molecules or atoms covalently bound amongst each other. In many cases, this could be a three-dimensional system. So diamond, for example, is a three-dimensional network covalent of carbon atoms, but it doesn't have to be three-dimensional. For example, graphite is a two-dimensional network of carbon atoms. In the case of diamond, the carbon atoms have sp3 hybridization, so each carbon atom is bound to 4 other carbon atoms. But in graphite, it's only sp2 hybridization, where every carbon atom is only bound to 3 other carbon atoms. The other thing that can happen in a network covalent is that it's made of a compound. So something which is binary, such as silicon dioxide, SiO2. So silicon dioxide forms a network covalent similar to diamond, but it's not quite the same. The network itself is a little bit more complicated, but it has many of the same properties. For instance, when you think about silicon dioxide as a network covalent, one of the results of that can be glass. Glass is a network covalent of silicon dioxide. So it has many properties similar to diamond, but obviously it's not quite the same. It's a different compound, a different network. Now, one consistency amongst network covalents is the property of hardness and high melting point. Hardness, because these atoms are bound together covalently. Now, that's a very strong force of attraction overall. And because it's in a network, there is an entire network system of strengthening that goes on. So if we look at graphite, for instance, the sheet of graphite that's two-dimensional is actually very weak compared to itself. So it sloughs off very easily. That's why we can write with pencil. But if we were to look at each layer of graphite, it's actually very strong. We're actually using similar network covalents now in the form of something called graphene, which is a very, very functional network covalent of carbon that has a lot of potential utilities going forward in the future. So in general, network covalents are going to be hard and have high melting points. Okay? And in general, or for what you're going to see, almost all the network covalents that we are presented in this course are going to be carbon or silica based. The second type of substance that we're going to look at today are polymers. Now, polymers, as the name suggests, are made of many monomers. So a polymer is something that you might have learned about in biology, where things like waxes, lipids are all comprised of smaller subunits. All right, same thing with proteins, nucleic acids. These are all comprised of smaller subunits. So if I'm a nucleic acid, I'm actually comprised of many nucleotides. If I'm a protein, I'm comprised of many amino acids. So when we look at these, they have very specific properties based on the fact that they're comprised of so many different smaller molecules. In polymers specifically, there can be interactions between different parts of the molecule. So proteins are a great example of this. Proteins have processes of folding, twisting, and rotating between the primary, secondary, and tertiary phases or stages of the protein development. And in these processes, bonds are not created nor destroyed, but interparticle forces are. And so the interparticle forces or the intermolecular forces are actually happening within the molecule itself and not between molecules necessarily. This is what actually gives a protein its tertiary and quaternary form, is the ability to rotate and morph using these intermolecular processes, but within the same molecule. So let's look at alloys. Alloys are metallic compounds comprised of different elements of metals put into the same compound. What this means is that you could have either a substitutional or an interstitial alloy if the metal atoms have the similar sizes or dramatically different sizes. So if one metal atom is significantly smaller than the other, it's going to be an interstitial alloy. And if they're about the same size, they're going to be substitutional alloys. Because they're all metals, though, they do share many qualities, such as conductivity. So even alloys tend to be conductive because they're still experiencing a sea of electrons. Where these alloys differ, though, is in terms of the other properties, melting points, and their ability to be malleable or bend, their ability to be ductile or put into a ribbon, or not a ribbon, a wire. Okay, so those are the properties that alloys can differ. And so we create alloys specifically in order to be able to exploit the different properties of the different metals involved. In general, interstitial alloys tend to be harder and more brittle, whereas substitutional alloys tend to be softer and less brittle, more malleable. All right, and again, that's based off of simply how those atoms are able to interact with each other and move past each other in the processes of melting or bending. So let's summarize today's video. Today we looked at network covalents, polymers, and metal alloys. Remember that network covalents are comprised of compounds or atoms that are covalently bound together in a network. Therefore, they have extremely high melting points, are very hard, generally speaking, and it's because of those covalent bonds, which are extremely strong force of attraction and become even stronger when put into a network form. We looked at polymers, such as proteins, where you have interactions within the same molecule that give rise to the overall tertiary and quaternary structures of the proteins. And we looked at alloys, which are comprised of different metal elements put together, either in an interstitial form or a substitutional form. And we looked at the properties associated with those. I hope you enjoyed this video, and I'll see you in the next one.